Hi, this is Kaundinya again, and today we are going to learn Boolean algebra. So, what is Boolean algebra? Boolean algebra is a branch of mathematics dealing with expressions of logic functions which are mainly in two states, that is, true and false. In digital circuits, these two conditions are represented by 1 and 0 depending on the logic employed. So, in the case of the positive logic, true we represent with 1 and false we represent with 0, and in the case of negative logic, true we represent with 0 and false we represent with 1. That is a reverse version of the positive logic. In Boolean algebra, we use three basic logic functions. They are, the first one is AND, and next one is OR, and the third one is NOT. And now this AND function, this is represented by dot. So we represent AND function with a dot, and this OR function with a plus symbol, and NOT symbol. NOT means a negation, so we represent with this symbol, or this one. So this negation and complement we call it now. So this is not. So we can see this example. For example, we say A and B, so it is represented like this. So here this is A and B. So when we say A or B, we write like this: A or B. And now if we say A complement, then we write like this, or A not, like this, or we can write this one even like this. So I repeat it again. Here in the basic logic functions, AND, OR and NOT, and this AND is represented with a dot, OR with a plus symbol, and NOT with this. Now we will see the basic postulates and theorems. So here we go. The first one, Boolean algebra defined over a set of two elements, that is, B is equal to set of 0, 1. So in Boolean algebra we use only two elements, that is 0 or 1. So this obeys the closure property, that is, the output of any Boolean function belongs to B. So the output belongs to B. So this results in closure property. Now we will see the postulate 2. In Boolean algebra, x plus 0 is equal to x and x and 1 is equal to x, that is x or 0 is equal to x or x and 1 is equal to x. This establishes two identity elements, 0 for plus and 1 for and. According to the postulate 3, x or x complement is equal to 1, x or x complement is equal to 1 and x and x complement is equal to 0. So this is the postulate 3, that is x or x complement is equal to 1 and x and x complement is equal to 0. And now, before we go into the other theorems, let me explain you what is this truth table. So, truth table, it is a table which has all maximum possible combinations of inputs for an output. So, for a given input, we give all the possible outputs. So, this can be shown in a table called as truth table. Now, we will see the theorems one by one. Theorem 1. The first one is x plus x complement is equal to x, or we can say it as x and x is equal to x. So this is the first theorem which states that x or x complement is equal to x, or x and x is equal to x. So if you want the proof, we can prove it using this truth table. We will see it how. So first we will take it. So what are the variables we have? We have x and we have x complement and the output y. So here we have only one variable, so we can take only 2 digits. So first we will take it for 0, and now we are going to, so a complement of this is 1 and the output y 0 plus 1, so that results in 1, so sorry 0. Now we will take it for 1 and the complement of it is 0 and the output is 1. So I will show you this one. Here, this one you can see it here, x and this the result y, these both are identical. So by this we can prove that x or x complement is equal to x. So in this way, using truth table, we can prove these Boolean functions or expressions. Now we will see the second theorem. So theorem number 2, that is x plus 1 is equal to 1 or x and 0 is equal to 0. So as I have said earlier, we can prove even this using truth table. So we will see it even for this one. X here, and the second one 1 here, and now the output y. And remember, this y is equal to x plus 1. So here x will take it as 0 and the 1 will represent it with 1, and the output y, that is equal to x plus 1, that is 0 plus 1, that is 1, and now we will take 1, and now here it is obviously 1, and the output is also 1. So remember this is very useful while we solve this Boolean equations. Whenever we are whenever we have a 1 with any variable, the result is always 1. So whenever we are adding 1 to any variable, the result is always 1. Now we will see the third law, that is involution law. So this is involution law, which states that x complement of whole complement is equal to x. So this is the involution law. So even this one we can prove it using truth table. I will show you. So let us take x first, and now this x complement and this x complement whole complement. So this is equal to y. Now we will take for 0, the complement of it is, yes, you are right, that is 1, and now the again this x complement is what we got it as 1. Now again we do the complement for it, so we get again 0. Now we will take it for 1, complement of it, yes, you are right, it is 0, and now again we are going to take complement, so we get it as 1. So you can see it here, this one and this one, they are same. So x complement whole complement is equal to x. Now we will see the fourth theorem, that is commutative law. So we will see this commutative law. So according to commutative law, x plus y is equal to y plus x. So this is the commutative law which states that x or y is equal to y or x, or x and y is equal to y and x. So as I have said earlier, we can prove even this using this truth table. So you can try it as an exercise. Now we will see associative law. So what this associative law states? It states x or y or z is equal to x or y or z. So associative law states that x or y or z is equal to x or y or z. So and it can be also stated as x and y and z is equal to x and y and z. So I will underline it here. X and y and z is equal to x and y and z. So this is x. Okay. So this is our associative law. Now we will see distributive law. So now we will see distributive law. So now what this distributive law states? It states that x and y or z, this is literally equal to x and y plus x and z. So x and y or z is equal to x and y plus x and z. So this is our distributive law. So it can be also stated as x or y and z, this is equal to x or y and x or z. So this is our distributive law. So as I have said earlier, you can prove this using our truth table. So now we will see this De Morgan's law. So it states that x or y whole complement or whole bar, that is equal to x complement and y complement. So this is a very important law we use while simplifying these Boolean equations. This has great importance in our digital electronics. So observe this carefully. Or this law, it can be also stated as x and y whole bar. I am writing bar because you need to get used to both of the notations. That is equal to x bar or y bar. Okay. So I repeat it again. X or y whole complement is equal to x complement and y complement. The second one is x and y whole complement is equal to x complement or y complement. So this is very useful while simplifying, because see here, you will get to know when we get familiar with this logic gates, but it's of no harm. You observe this. Here you can see it. We have OR symbol, but we need to simplify this equation or simplify some problem using only this, and then we can use this De Morgan laws and we can simplify that. Got it? Here you need to simplify a equation and you need to get the result using this and OR symbol, but we have only AND logic gate. Then by applying this De Morgan laws, we can get our result. You will understand it in a better way when we get familiar with these logic gates. That is in the next sessions. Now we will see this absorption law. So what this absorption law states? It states that x or xy, this is equal to x. So want to know how it is equal to x? I will prove it. Wait. So we are fed up with proving it using truth table. I will simplify it and I will prove it. Okay. So now how we can write this one? So I will take this x as common. So what we have? 1 plus y. So I took this LHS and now I am proving it. So what we have? I took this LHS. This 1 plus y, as I have said earlier, whenever we are adding something to a variable, it always results in, say it loud please, it always results in, yes, it always results in 1. So now this gives rise to x and 1, that is x, that is equal to RHS. So hence proved. You know one funny thing, probably even you must have done this one. In mathematics, when they give some proofs in our examinations, we used to solve it, we used to take LHS and we tried to solve it from top to the bottom. We will get stuck up somewhere else, then we will take the RHS part at the down of the page and we will go in a reverse order, and at last we used to write hence proved. But you know, all that gimmicks, we don't need it here, because these Boolean equations, they are really simple. What all you need is, as I have said, all these 8 theorems. If you can excel all these, if you can excel in these 8 theorems, then you know It's really easy. My dear friends, now we are going to jump into my favorite theorem. You know, this theorem is really juicy, funny theorem. It has a great importance in Boolean algebra. So now I present you this theorem named consensus theorem. So now we will see what is this consensus theorem and why it is juicy or a yummy theorem. So now we will take a Boolean expression, that is AB or A bar C plus BC. This results in AB or A complement C. You can observe it, we have skipped this. Why we have done like that? We will see it. Now, in a simplification of this Boolean expression of this form, that is here a variable and a complement of the same variable and the two other variables. Okay, a variable, complement of the same variable and two other variables. And we need to see that these two other variables must also be present here. Then this variable, this one, that is the BC, it becomes redundant. So we can skip this and it results only in AB or A complement C. Still not believing my words? Okay, we will see the proof now. Proof. So our given expression is AB plus A bar C plus BC. Now take it in such a way that every term contains all the variables, that is every term must contain all the three variables A, B and C. So how to take it? Simple dude, I will tell you how. A, B, now we need C here. So I hope it's of no harm taking in this way, right? C plus C bar, sorry, yes, no harm, because this results in 1. And now in a similar fashion we will take it here also. So what is the missing variable here? It is B. So take in this way. Repeat it here also. And now the next step, expand this, that is what we get? We get ABC bar plus ABC plus A bar B bar C plus A bar BC plus ABC plus A bar BC. Now observe this carefully. Can we reduce it still further? Yes dude, of course we can reduce it, because see it here, Here we have one ABC term and another ABC term. As I have said in this theorems, what we had? A plus A. What is this? Sorry. No, it's okay. A plus A. That is equal to A. So we can implement it here, right? So implementing this, we can reduce these two terms, this one and this one. So we can make it as one term, and we have it even we have it here also. So from these 6 we can make it into 4. So what do we get? We get it as ABC bar plus ABC plus A bar B bar C plus A bar B C. Now we can ignore these two because I have said earlier now we have taken it here and here, so ignore this. Ignore I. And now how can we simplify this further? Think, observe it here. We have ABC and ABC bar. Where do we have? ABC bar. Okay. So here we can take AB as common, and here we have A bar C, B bar and A bar C, B. So here we can take A bar C as common. We'll do it. So what do we have now? We are going to take AB common, and this one is the first one, and next we are going to take A bar C as common. And now it's almost simplified. I hope you are able to see the answer in this. Yes, this one always results in 1, and even this one always results in 1 and only 1. So the result is AB plus A bar C. Very simple, right? Oh, we have got this RHS. This is equal to RHS. So at last what we should write? Hence proved. I don't know about you, but I really feel satisfied when I write this. Hence, my dear friends, do you know the key characteristics of our electrical and electronic engineers, or any engineers in particular? You know, they are really conjuice. That is, they try to, or they tend to spend less and they expect more. So if you want to become a good engineer, you need to adopt this property. Now the reason why I say this, you can see it in this class, because now see this expression. Now here we are given an expression that is A or A complement B or A B complement. So this is our expression. So if we are strictly going to implement this expression, then we need 1, that is 1 plus 1, 2 OR gates, 2 AND gates and 2 NOT gates. So totally we need 6 gates, right? As I have said, our property, our engineer's property, we try to spend less and expect more. So how to reduce this hardware cost? That is simple. If we want to reduce our hardware cost, then we need to reduce these terms, means we need to reduce. So all the Boolean expressions, they can be reduced to some extent. So here we have simplified this one to a plus b, since we have this property as a plus a bar b, this always results in a plus b. So we can write this one like that. And now here you can see that here in these both we take a as common. So what do we get? 1 plus b bar plus b, that is this term. Now what do we have? As I have said earlier, 1 plus anything always results in 1. So a plus b. See, from 6 gates to, we have reduced it only to 1 and only 1 gate. So more gains and more profits, right? We have reduced the hardware. So my dear friends, always remember, economics is not always in the hands of the economists, it's always in the hands of the engineers. So we are going to reduce the cost of the hardware or the software, and we are the one who are going to increase it. So in this world, always engineers are the king makers, and be proud to be an engineer. So now coming back into our subject. So we can reduce a Boolean expression into the simplest format. So we can use 4 methods to reduce a Boolean expression. The first method is this algebraic method. The next one is simplifying using K-map or corner map. The third method is Q-Mikulski method, and the fourth method is variable entered method or tabulation method. So, and this even this algebraic method is also called as this Boolean law method, because we are going to simplify it using Boolean laws. We will see this one by one. Now we will see a problem using this Boolean laws and algebraic this thing. So here we are given an expression, there is AB plus A C bar plus A B bar C, A B plus C, right. This is a given expression, and now we need to simplify it. So how we are going to do this? So we will do it step by step. Now here we'll take this one. This can be still expanded as AB plus, yeah, using this De Morgan laws, this can be written as A bar plus C bar, right? We used the De Morgan law. Now expand this. What do we get? ABC AB plus AB bar C C. So here observe this. Here we have B dot B bar. Okay, B bar dot B. So what it becomes? It becomes 0. Yeah, anyhow we have A and A, so we can reduce it one, but still here consider this one. B bar and B, what it becomes? It becomes 0. So totally this term becomes 0. And here we have two C's. C dot C, that is equal to C. So it almost got half reduced. So we have this one. Now let's not touch this one. This, for the God's sake, it becomes 0. And now here it becomes A B bar C. And now what we are going to do? Here you take A as common in this both. Take A as common. So we are going to take A as common. It gives B plus B bar C plus A bar plus C bar. Now in the previous problem I have said, this B plus B bar C, this results in BC. Always remember this one. I said it earlier, but still remember this. So this gives us A into B plus C plus A bar plus C bar. So I'll write it here. I'll continue it here. So what it results in? Now expand this one. It gives AB plus AC plus A bar plus C bar, right? Now see this, AB plus A bar. Now take, now take this as one term and this one as another, this thing. So what do we get? It results in, now this one, AB plus A bar. This results in A bar B. A bar plus B. Sorry. Understood how? Normally we have here B plus B bar C, but here we have here complement and here we don't have a complement in when we consider this case. So it results in A bar plus B. Now we take this AC and C complement, right? So what this results in? This results in C complement plus A. Understood? So finally this gives us 1 plus because A plus A complement, this gives 1 plus B plus C bar, and finally this gives 1 because 1 plus anything gives 1. Remember, here I don't mean this to be this thing, but this is not complement. To represent, I have marked it here. This is not complement, okay? Even here. So here we have taken this as one pair and this as one pair. We have simplified it. Finally, we got the answer as 1. See, you can see here how much huge expression we have it here. And finally, when we simplify it using one or the other method, using this K-map or this Boolean this thing or Q-Mikulski or tabulation method, you can simplify it into the simplest form. The reason is simple. We need to reduce the number of gates, and we have done it here. So problem solved. Now let me give you an exercise problem for you. So here is our expression. A bar, B bar, C bar plus A bar, B, C bar plus A, B bar, C bar plus A, B, C bar. So I repeat it again. Our given expression is A bar, B bar, C bar plus A bar, B, C bar plus A, B bar, C plus A, B, C bar. Now simplify this expression and get the result. And that's it for today. And this is your Continuum signing you. Goodbye.